Hello and welcome to today's MOBEX webinar. My name is Elle Farrell-Kingsley. I'm part of the editorial team here at Automotive World and I'll be your host for today's session. Today's panel is brought to you by our knowledge partner, HiveMQ, and we will be looking at bringing hyperconnectivity to hypercars with MQTT and Kafka. Leading us through today's session will be our expert speakers, Luka from Rimac Technology and Gura from HiveMQ. As always, we will finish with some audience Q&A, so do send in your questions and we'll get to them towards the end of the session. You can ask a question at any point by typing it into the Q&A box on your screen. After the presentation, we will also send you the slides and a video recording of the event. And with that, I will hand you over to today's expert speakers who will get us started. Over to you.
Thank you, Elle. Appreciate it. Welcome, everybody. Before Luka starts to share the work that Luka and team are doing at Rimac Technology, I would love to give you a quick introduction about HiveMQ. We are a company which has been in operation for more than a decade now, and we are headquartered just outside of Munich in a city called Landshut in Bavaria, Germany. We serve multiple industry verticals, but the particular call out we want to give for today's presentation is for the OEMs and tier one suppliers who are using our technology to build reliable and scalable connected car services. And that's what's helping them drive new customer experiences and also build new revenue opportunities. We are extremely proud that more than 130 customers across the world are trusting us to build solutions which gather data from endpoint and their edge. We have been in the news lately. If you've been watching us, I guess, we did a recent Series A round of about 40 million euros earlier this year, and we continue to scale and grow our business thanks to our customers, of course. So Luka, if you don't mind moving to the next slide here. And after this slide, I'll move it to you, Luka, so you can start your presentation. This is just to mention to the people attending the fact that the customers that HiveMQ is serving is building new digital product based on our technology, with the help of our technology, improving customer experiences, building new efficiencies, and discovering insights to their operations. Our customers are across multiple verticals. One of the stories we'll hear today and the expertise we'll hear around our technology today and how it's helping Rimac Technology meet their goals is what Luka will be walking us through. Luka, over to you. Thank you so much.
Thank you. So hey, everybody, first of all, thanks for joining today's webinar. And before we kick off, I'd like to just say a word about me and the Rimac Technology. So as you know, I'm Luka. I've been working for Rimac Technology for the last 4 years. And most of the time I'm working on, as we call it, vehicle connectivity project with technologies like MQTT, Kafka, Node.js, Scala, and GraphQL. And before every presentation, I usually like to set myself up with a few personal goals of what I want to actually achieve on each presentation. So for this presentation, I would actually like to try to expand the Rimac Technology's presence as a software powerhouse, since besides super cool cars and various battery systems, we are also building high-level software and nobody actually knows about it. So that's our main goal today. Also, to give you an insight of what are we actually trying to build from the project side and what problems are we solving with our project, and how are we actually achieving that using MQTT, Kafka, and other technologies. Okay. So as you probably know, Rimac Automobili or Rimac Technology, they're actually no longer the same company. So Rimac Automobili actually is now strictly building vehicles. And Rimac Technology is a Tier 1 OEM supplier of technologies to various OEMs, including Rimac Automobili. And as Rimac Technology, we are building various solutions from battery management systems to cloud software solutions. And regarding one of them, connectivity platform, we'll actually be talking about today. So when people think about Rimac, usually they think about, and the first thing that comes up to their minds is actually these beautiful hypercars. So on these slides, you can see the Rimac Nevera and Bugatti. I think this was Mistral, the new one that actually we presented a few days ago. After that, after super cool cars, people think about and correlate Rimac with some kind of battery solutions that we're actually building and selling to other OEMs like Koenigsegg and other. And beside the things mentioned above, the last thing that people actually think about us is that we are building some kind of ECUs, like battery management system, the whole hardware package of it, the IVI in-vehicle infotainment, and actually the TCU, telemetry control unit, which we are actually using in our system. But very rarely does anybody think of a solution, especially a cloud solution that Rimac is building, and especially a software solution built with TypeScript, Node.js, GraphQL, Scala, AWS, MQTT, and Kafka. So for today's presentation, I'd like to actually present to you guys what are we actually building, especially those cloud technologies that I just mentioned half a second ago. Awesome. So what are we building? So we are building something called Connectivity Platform, and in short, it provides a two-way communication with a vehicle and our cloud system. It provides various APIs to actually retrieve the data sent by the vehicle, and also it provides APIs to manipulate the vehicle itself. Besides sending some remote commands to the vehicle to unlock itself, horn, or maybe even drive via remote commands, and also to configure its configuration. So we can actually manipulate what kind of software update is currently available on the vehicle, what is the configuration that is going to be sent via telemetry to our system, and stuff like that. Okay, so in few, let's say, visual pictures, I'd like to demonstrate you how does the platform actually work. So from the left side, you can actually see vehicles that are using our electronic control unit, or as you call it, TCU, telemetry control unit. It can be seen on the bottom left corner of this picture. And the TCU is actually the one doing the communication with our platform. And it sends all the data to the platform where it's permanently stored. And from the other side, we actually provide APIs. So these custom APIs or custom projects that anybody wants to build can actually connect to our APIs and build whatever they want. And we have a few of those, let's say, custom projects that are built upon Connectivity Platform. And the two most prominent of them are OEM dashboards. And it's actually an internal monitoring tool that is being used while the vehicle is under a development phase. So the main problem that we with the OEM dashboard are trying to resolve is when the vehicle is under development and you test it on some kind of a track, it's really hard when something goes wrong to actually debug the vehicle and see what is going wrong. And usually most of the time you need to reproduce it. But when you're talking about vehicles that are up to 3 million euros expensive, you don't want to reproduce the same bug to have the same consequence on the first time. So OEM dashboard actually provides a nice visualization and analyzing tool to actually see in depth what is going on with the vehicle and actually improves the development process quite a bit out there. Other, let's say, project that we are building is the mobile app for the owners of the vehicle, so they can actually see some kind of statistics, driving sessions where they were being driven their vehicles. And also they can manage or let's say schedule their own software updates when it's available for their vehicle. Okay, and before we dive into the technical architecture of each functionality, I'd like to discuss what exact functionalities and metrics are we trying to achieve with our platform. As we started out as a startup, we didn't actually know what we were doing. We didn't have all of these, let's say, specifications that I'm going to just show you. We just started to build it step by step. And then after like 4 years of development, we came up with us, let's say, set requirements that we strictly want to accomplish with our solution. And those are actually, we want to build something that can connect a vehicle to a cloud system. We want to configure telemetry data options. More specifically, we want to define what kind of data each vehicle can send and with what frequency. I'll talk about later why this is very important to us. Also, we want to build something that can receive remote commands sent by the cloud system and upload telemetry data near lifetime. It must be fault tolerant to any data loss. Also going to talk about this one in more details later. And we want to be able to, let's say, receive over-the-air software updates sent by the cloud system or cloud engineers, whoever is actually operating the system underneath. So how are we building it? We chose MQTT and HiveMQ broker because it's actually lightweight and fast. It supports bidirectional communication with the client. It can easily scale up to tens of thousands of clients. It's reliable in message delivery. It's fault tolerant, meaning if for some reason something goes wrong with the system, let's say for example, if the data wasn't successfully transferred from HiveMQ to let's say Kafka, because Kafka was down for any reasons, the data won't actually be lost. It will be contained inside the HiveMQ and is going to be processed later when the Kafka or any other service consuming the messages from HiveMQ is actually back and alive. And also, Kafka HiveMQ out-of-the-box extension is one of also the main reasons why we chose exactly HiveMQ broker for MQTT, because it provides us, let's say, automatic mapping. So if something is delivered to MQTT, we don't need to code ourselves anything regarding, okay, so we send something to MQTT. We don't need to think about and code anything where it should be sent to Kafka. We just need to configure the existing code or existing configuration, and it works out of the box, and it's supported by HiveMQ team. Okay, and regarding Kafka, we chose Kafka, especially MSK Kafka. Well, it's a highly scalable solution. It enables high throughput, which is really important for us, especially when we're talking about sending a lot of signals from a lot of vehicles with a lot of, let's say, frequencies. It's fault tolerant, which meaning it can make sure that any microservice reading the data or consuming the data from the Kafka, if something goes bad with it, nothing will actually go wrong, because after the microservice connects again to the system, the Kafka knows that it needs to, let's say, save the data for it, and it won't process it any later. Also, it is distributed, high concurrency, meaning it can handle thousands of messages per second. And when you combine HiveMQ and Kafka side by side, it provides us with a really scalable and let's say bulletproof solution. At least we want to think it's bulletproof, that provides us with sending the data to the system and receiving the data from the system to the vehicle itself. Okay, so just to go through some kind of a few slides regarding our architecture. I'm going to show you 4 or 5 slides to demonstrate you how do we actually provide our key features of the connectivity platform. So in this architecture, we can actually see that upon connecting to the system, sorry, the vehicle is sending its config to an HiveMQ dedicated topic. And then out of the box, we have Kafka extension, as I talked about, actually a plugin or extension that knows how to read data from HiveMQ and knows where exactly and how to transform it and proxy it basically to the Kafka cluster that you have connected to it. After the data gets sent to the telemetry config topic, we actually have something called data format service. What is that? It's actually a Node.js application that reads the, let's say, the configuration of the vehicle and saves it in some kind of a storage. Why is this important? Well, with this feature, we want to know what exact capabilities are available by the vehicle itself. So if we are talking about, let's say, Hyundai or Rimac or Porsche or any vehicle, usually signal names are not the same. So the information that the vehicle wants to send to the system is not the same. So something that is conceptually, let's say, speed, how fast is the vehicle going, one vehicle or one model of the vehicle. So if we have a Nevera and a Nevera 2, the future one, it's not going to be named the same. So this one might be named in English and the other one might be named in Croatian. So we need to know exactly what kind of signals can the vehicle send. It needs to identify itself to us, and then we can actually provision that configuration, and then we can also set up with how much frequency do we want each of those signals to be sent, or do we want the vehicle to send it at all? Because usually in vehicles you have multiple sources of the same information. So you have speed defined on 5 different ECUs, and you can actually send all of those 5 speeds, let's say so. But it's totally, let's say, bandwidth not efficient. So we literally want to know what vehicle can do, what the exact signals can it send, and we want to be able to configure. Okay, we want the speed to be sent with 1 time per second, and maybe GPS like 2 times per second and stuff like that. And after we actually provision the data format, after we know what we want, how we want the vehicle to behave, we actually send the configuration back to the vehicle, also through Kafka, to, let's say, configure data format topic that actually is getting read by the Kafka extension and sends it back to the vehicle. Oh, sorry. Okay, and then after the vehicle actually knows what it needs to do to send the telemetry data, each vehicle sends its data to a specific telemetry topic dedicated only for him. And then Kafka also reads the data from those topics and sends it to Kafka telemetry topics. Then we have something called telemetry processing service, which is nothing but a Scala service that actually decodes the data, since it's encrypted, it's in Proto and other stuff, and it stores it somewhere on the system, so it can be used later for any kind of operations, calculation, statistics, and anything that is needed by external teams to operate on. Okay, so as you can see, as you mentioned, as you can maybe seen it by now, all of these, let's say, architectures are pretty much done with the same boilerplate. So from you have HiveMQ connected to Kafka, and then connected to some kind of backend microservice or service, and then maybe some kind of a client sending, let's say, requests to the backend and vice versa. So each of them are quite similar, but with a little bit of tweaks regarding how the data actually flows through the system. And when we're talking about receiving remote commands, we actually, from the right side, have some kind of a client. It may be a mobile client, web client, dashboard client, let's say PC client, whatever, that actually sends a request to do something with a vehicle. And after that, it gets sent back to Kafka cluster and all the way back to the vehicle. After the vehicle validates the message, after it, let's say, defines what it needs to do, and after it does it, it sends an acknowledgement back to the system all the way through, same with the same flow, all the way back to the client. So the client does know that the message actually executed and the vehicle did unlock, or it did horn, it did move 5 meters forward, or whatever the initial command was actually designated for. And one of our last, let's say, big features is that we wanted the vehicle to be able to receive over-the-air software updates. Also, this one is pretty much the same as the previous ones, with a little bit of a extension. So from one side, it works the same as remote commands. There's some kind of a system that actually sends the software update to the vehicle. The vehicle reads it from its own specific update topic, but the main packages from, and I call it here downloadable entities. So these links are, so these real binaries are actually available to some kind of a, online cloud system, and that's, those
I'm
are
sorry to interrupt
protected.
you, Luka.
I'm sorry.
So for the last about 30 seconds, your audio got a little choppy. So if you don't mind just repeating what you said for the last 30 seconds, please.
Oh, sure. Do you want me to go from the beginning of the slide or the previous one?
Yes, this one.
Okay. So regarding software updates. So we wanted to provide some kind of a feature that we would like the vehicle to be able to upload itself with a new software update that is designated for him. So the same way as our mobile devices work at the moment. So you get a notification, oh, hey, you have a new update, please set some time up to update yourself. We wanted the same feature to be available for our vehicles, and how we manage this is actually through the same remote commands flow that you saw previously, but with a little bit of adjustment. So the flow goes as next. So when somebody is actually we call them, let's say, order update engineers, and somebody defines what exactly goes on each, let's say, hardware of a vehicle. They need to create some kind of a package, and when they create a package, two things happen. So from one side, we actually upload all of those packages that are going to be downloaded by the vehicle to some kind of a cloud system that only that specific vehicle can access for a let's say temporary amount of time, and of course with credentials. And to the other side, directly to the vehicle, we send the vehicle through the same flow. Through Kafka and through MQTT to specific MQTT topic. We send the vehicle the links from where it should start downloading its software update. And after the vehicle starts downloading its software update and it finishes downloading the software update, it actually sends back an acknowledge that it finished downloading its software update, and then it can actually, let's say, get the process of installing the software update. So the main question here is why we actually extended the functionality to add this cloud service from the vehicle to download the software from. It's just the main reason there is that software updates of a vehicle can be pretty big. I'm talking about up to 10, 20, 30 gigabyte in size, and we didn't want to send that amount of data through Kafka and MQTT. It's technically pretty much impossible. So we decided to send on the links from where the vehicle should download its updates from, and then the vehicle can actually download it when it's on Wi-Fi or in garage home or with a good enough connectivity. It can download the updates from and install it by its natural installment flow. Okay, and this is all good and what I showed you, but the main power here comes with, let's say, what can we actually use when we have a system like this? How can we actually use this system, and how can we build something meaningful? It's good enough to have a vehicle that can connect to some kind of an online system and send its data there to receive the remote commands, to receive software updates, receive anything, send anything. But how do we actually use it day by day? So I'd like to show you now two main of our internal projects. So I talked about a little bit about them in the beginning. So we are talking about OEM dashboard project, which is a fleet management tool. It has the ability to analyze telemetry data. It can manage over-the-air software updates, and it has the ability to preview live data of the vehicle. So just a few slides of how it actually works and looks like. You can see from the bottom left corner, top left corner, sorry. This screen is actually the live data preview. Why this is pretty useful is, let's say, in some R&D phase, the vehicle is under development, and you are constantly testing the vehicle on some kind of tracks and even highways. Most of, let's say, engineers are not near the vehicle at that moment, but they want to know in live, let's say near live time, they want to get information what is going on with the vehicle. So in the top left corner, you can see something that we call is our live data playground, where each engineer can actually, let's say, set up its own some kind of widgets that he can get notified really quickly about if something is going wrong with the vehicle, how fast is it going, did some temperature spike or not. Basically, it's a live preview of the current state of the vehicle, what's going on with it. On the bottom left corner, you can actually see our fleet management preview, so pretty much a home screen to actually see what all of the vehicles in the systems are, where are they, or where they were the last time it was connected to the system, and how were they behaving. Did somebody be speeding or something like that? Pretty much was it behaving in normal way as it should have been. In the bottom right corner, you can actually see when you dive into analyzing a vehicle, you can actually see each trip specified. So what was the length of the trip, or the session, what was the max speed of the, let's say, various statistics of each trip. And then I also have one on full screen. This is actually the main tool that everybody is using. So when the vehicle is under development, as I said, it's really crucial that you can dig into the data. You can actually see in milliseconds of accuracy what was happening with the vehicle while it was, maybe speeding over some kind of speed. So you can, on this screen, you can see that the vehicle was actually going over 200 kilometers per hour. And at that time, some kind of voltages and battery information was sketchy. And this actually helps the engineers to debug the system a lot. So you can analyze, why did my, I don't know, let's say the temperature of the battery spike up specifically in this corner where I was driving 55 kilometers per hour, and they can do it while not even being close to the vehicle, which is the process, the development and the debugging while it's under. And the other internal application that we have is Nevera mobile application. This application is strictly used by the owner of the previous application. Is used only while the vehicle is still not sold. While the vehicle is in production phase, in the development phase, sorry. And those vehicles actually don't have owners. So our proto vehicles and mule vehicles, as we call them, and we are developing them and testing using OEM dashboard. And when actually you get to series production, after those vehicles get connected to our system, we have mobile application that are being used by owners of the vehicles to have some sexy views, to offer remote commands, to track activities, to control your climate options, to, let's say, manage your battery options. And this is, let's say, a super cool idea and super cool features of a new age vehicles. So imagine, like, it's going to be really cold tomorrow morning, and you need to go to the car itself. Using this mobile application and our connectivity platform, you can actually schedule up for the vehicle to be ready with the temperature line on a heat up to 20 degrees, and to be everything to be ready for you when you enter the car itself. And pretty much, I wanted to, let's say, a little bit speed up with the architecture, since I'm pretty sure you guys will have a lot of questions that I would like to answer most of them. Regarding any resources, how to start with HiveMQ, actually Hive to enable the IoT world to HiveMQ or connect the car to HiveMQ, please search these links and resources that are on screen, and feel free to ask any questions on our mails. And once again, thanks again for listening. Hopefully it was, let's say, a little bit educational and fun to listen to our story and what are we actually trying to build at Rimac Technology.
It was fantastic, Luka.
Sorry?
Go ahead.
We now have time for the Q&A, so do get your questions in. A quick reminder that you can ask a question at any point by typing it into the Q&A box on your screen. Just also another reminder that everybody will receive the presentation slides after 24 hours. And thank you to everyone who's already sent in a question. So we'll go to the first one, which is, what are some of the cautions when taking on an innovation project such as yours?
Well, to be honest, since we started it 4 years ago, this project actually started as an idea from Mate himself, since he was pretty, let's say, frustrated with the idea that every time something bad happens with the vehicle, you literally had to physically get to the vehicle, connect yourself with a cable to it, download a bunch of textual data, and start digging through it. And Mate was pretty, let's say, pissed that he literally told us, hey guys, how come a simple coffee machine can connect to some kind of a cloud system and start communicating it, even start cooking coffee with a mobile application, and why don't we make it with a vehicle that's 2 million euros, let's say, expensive. So the things to be cautious about is IoT is a big, let's say, sphere. And the main problems that we are encountering with is the connectivity issues, and in the areas that the vehicle or the client, whatever it is, it may be a refrigerator or the vehicle itself, when it has a low connectivity, let's say, internet access, then you can do anything basically, and you have to account how to manage those times and what to do when the client just doesn't send anything to the system.
Perfect. And you appear to use lots of open standards technology in your tech stack. Is that a strategic decision?
Well, what we wanted to achieve is that we always wanted to use new technologies. So we didn't want to use let's say the old ones. We wanted to be up to speed with the technologies, but also we didn't want to use the newest ones because we wanted to use something that's stable enough for a long-term project, especially since it's hard to, let's say, find developers and resources in the new upcoming technologies. So we decided, let's say, with a set of technologies that we think are good enough, are, let's say, new enough and to work with, are quick enough to work with, but also we are pretty sure that they will be around us for quite some time.
And what kind of scale are you building for? And what are some of the risks that you might see with that growth?
So currently we are aiming for, let's say, this year to be able to connect up to a few thousands of vehicles to our system. But as years go, we want to be able to, if somebody comes to us, hey guys, we like what you're building, especially some OEM, if they come to us and say, okay, we want to connect in the next half a year, I don't know, tens of thousands of vehicles and maybe even millions of vehicles in the system, we want to be able to do it somehow easily. It won't be easy, but we want to be able to scale horizontally to do it. But our next goal is to actually be able to scale up to thousands of vehicles. And then after that, we can think about anything greater.
And is the telemetry data sent on the GSM? How does this process work? If you can describe it as brief as possible. I'm sure it's a very long explanation, a presentation in itself.
Yeah, so pretty much as I talked about, you have a TCU. This TCU, or the Telemetry Control Unit, that is a set of hardware built by our hardware team. It has an application on it or some kind of software, and it's installed. The hardware itself is installed inside of any car that you want, and it's listening to CAN interfaces. And after it listens to CAN interfaces, and then it gets the data that it needs, and then it sends actually the as I explained, the data through MQTT and goes through all of the flow that actually needs to go to be stored in the database.
Going back to the ECUs for one moment too, are the software updates for all the ECUs or ECUs specifically provided by Rimac?
Well, to be honest, we do handle all of the ECUs provided by the Rimac with our software updates, but also we have some software updates for ECUs not provided by Rimac. But I mean, if you buy some ECU that is, let's say, private and you don't know its source code, you can't update it. But if somebody, let's say, if we buy some kind of an ECU, and if somebody gives of the software update, we can upload it to the ECU. If there's nothing, let's say, specifically about the installment procedure for that specific ECU.
And is proprietary information available to the developers? So, for example, the command to heat up the car or start the car.
I wrote out this architecture in quite a high-level architecture, but not everybody can send, let's say, remote commands, software updates. Not everybody can see the data the vehicle has sent. So from the other side of the system, let's say you need to have specific permissions or applications, or so each application has specific set of permissions which defines what data can it read, what commands can it send, and to what vehicles. So for example, if you and I were users of the system, or maybe even let's say some kind of a front-end application, maybe your account could have access to read data from your vehicle, but my account can only read data from my vehicle and send command to my own vehicle. So not everybody can do that, especially not the developers, since we don't have let's say access to production vehicles themselves or production environment.
Perfect, thank you. So one question is, why would HiveMQ be a better option in terms of being cost effective instead of an open source or other cost effective software?
Well, to be honest, 4 years ago, we didn't start with HiveMQ. We started with, I think it was Mosquito, not sure. On your first implementation, yeah, you think it's more cost effective since open source, it doesn't cost any licenses. But when it comes up to the need of scaling, when something goes wrong and when you need to fix the bug, when you need to deep dive into software that you didn't build, you actually need to dedicate a lot of resources or developers or DevOps to actually be experts of that that field or that technology. And when you just let's say combine or just look at the average salary of a DevOps engineer, senior DevOps engineer, or senior developer, and then look at the price that the HiveMQ is giving. HiveMQ price is way, say, less than a developer hours themselves, and especially they are really responsive on their side, and they built it, they know what it's for, and to have resources locally regarding let's say an outside technology, that's quite, let's say, expensive. Maybe not on the first site, but when it comes to scaling up, when something goes wrong, it really is beneficial to have an expert of the technology to know what is going on. So that is the main reason why we switched from let's say open source to HiveMQ.
That's very well explained. Thank you. If we keep the questions coming in, there's lots to still go ahead. So the next question is, what kind of two-way connectivity are you planning or already implementing into your solution?
So as we said, the vehicle can send its configuration, or as you call them, a list of signals. So its configuration to us. It can start sending vehicle telemetry data. It can send a lot of, let's say, acknowledges what is happening. It can receive remote commands, software updates. For the future, we would like to do something about implementing, let's say, streaming video. So if the car itself has some kind of cameras around itself, lidars or any other specific sensors, we would like to also be able to get the data from the vehicle to our cloud, and pretty much that's something that should be good enough to firstly think of to expand the system with.
And what about LEO satellites or direct-to-device satellites? Are there any plans to incorporate these in terms of your two-way connectivity?
Not at the moment. We haven't think about it now.
Okay. And if you were to use various hybrid infrastructures for connectivity, how would you manage the priorities and handovers between these network connections?
So I'm not sure if I understood the question correctly. Are we talking about how do we provide the solution to somebody that doesn't want it on AWS, and we provide it to maybe Azure or locally on their own virtual machine, or are we talking about how does the, let's say, telemetry behave when it's moving through different countries that have different, let's say, internet providers? So I hopefully it will be about the internet providers. So when the vehicle is actually moving or it gets shipped to the US, we actually have an eSIM installed into it, and we are in let's say using our creation company that actually provides some kind of a profiling for eSIMs. So when the vehicle notices that it's in, let's say, in America, it actually automatically gets switched to a new eSIM profile that is configured, and it's paid to be able to send data from America, or is it Europe or whatever location we're at. We do have some problems with China, of course, but we will think about what to do with that some other time.
Great. And so going back to the connectivity as well, How do you ensure that GSM connectivity is as stable as it can be?
Well, actually, we actually don't. We have a the main, when I talked about fault tolerance on each part of the system, so basically there's three parts of the system. You have the TCU or the vehicle itself, you have the HiveMQ, and then you have Kafka and our backend services. So each part of the system has some kind of a buffer. Let's say vehicle, if it cannot connect to any type of connectivity, whatever it is, it's a Wi-Fi or anything, it actually still, let's say, saves all of the telemetry data that it should have sent to the system. It actually saves internal storage, so it can be sent later when vehicle has connectivity. Same thing goes with HiveMQ. If something goes wrong with the Kafka, it knows, it saves the data on its own disks and actually sends it later on. And also Kafka on its own, let's say, knows about its consumers and won't actually commit any messages or delete them before all of the consumers that need to read the data have consumed the data.
So one user as well would really like to know, why Kafka, and did you try any alternatives?
Actually, no. From day one, we started using Kafka because it's highly distributed. It can take a lot of data, a lot of, let's say, different amount of messages, and we're used to it. We're used to the technology. Sometimes you just have to, even though there is something maybe available from the technology side, when you have a team of 10 to 15 developers, you just need to take into knowledge that these guys know this technology, and just learning the new technology can be quite slow process, and it might not be worth it. But mainly because we think that Kafka is the solution for this, especially when it comes to distributed system, high throughput, and fault tolerance. It works perfectly for us.
So the next question is there some form of issue regarding EMC?
EMC, I'm not sure what that actually means. Oh, electronic magnetic fields, or I'm not sure what are EMCs.
So typically it might mean electromagnetic compatibility.
Okay. I get it now. Okay. So we actually didn't test that one out. I do guess that something can happen, but if the vehicle is actually, if the TCU itself did, let's say, sample the data that needs to, it will eventually be sent. The data itself cannot be, let's say, corrupted by in any way, since it's read from the CAN buses of each vehicle. We haven't tested it out. If something can go wrong, maybe just the data won't be sent at all. But once again, it will be saved on the internal buffer of the vehicle, and when everything is fine, it will send the data eventually.
Perfect. Thank you. And one last question I think that we have coming in is, how do you secure the required bandwidth per car and fleet for OEM data traffic? And how would you secure it for customer/owner traffic? So the difference between, for example, SOT to the video calls and video usage.
Okay, so that's why we actually have something that we call the data format. So in the vehicle sense of the configuration, we can specifically say what data and what amount of data can each vehicle send. This is very beneficial to us because let's say, for instance, in the development phase, everybody wants to track everything with 100 hertz, so that's 100 times a second, and you're talking about gigabytes of data per second. But once the vehicle goes to production, there's no need to send the GPS 1,000 times a second. It just doesn't move like that. The values of the signal doesn't change. So with that system, we can actually configure strictly in what use cases or in what environment the vehicle should send what amount of data and how fast. And that also goes to the video, let's say, flow. We still didn't implement, as I said, the video upload. So, but it can be, I guess it can be managed with our data format functionality, definitely.
Okay, brilliant. I think with that, we could bring the Q&A to a close. Did you have any final comments you'd like to make?
From my side, no. Thank you, everybody, for listening. Thank you for the great questions. And hopefully I answered all of them correctly.
Brilliant. I think we can now bring today's session to a close. I'd like to thank our expert speakers for sharing their insights with us today, and also HiveMQ for supporting the event. Just a quick reminder that the presentation and an on-demand version of today's webinar will be made available to you within 24 hours. That's all for today's session, so thank you all for listening in, and goodbye for now.
Thank you.
Thank you, everybody. Bye.